So periodic trend, basically what I'm going to do is I'm going to take this worksheet and I'm going to review everything that we've done in Chapter 5. So we had 6 things that we really focused on in Chapter 5, and we had atomic radii, ionic radii, valence electrons, ionization energy, electron affinity, and electronegativity. Now, when you are watching this, this is while I am not in class, and so hopefully you can get this done, and then if you don't get it done in class, please finish watching it at home, and then when I come back to school on Monday, we're going to talk about it, and then we're going to do the other side of this. So there are 6 of them, but you're only required to do the 3 on the front for this particular section. So there's some things that I want to talk about in this, and this is a really good way to study. Once we're finished with this, you're like, oh, I get a lot of these things now. So again, you can't study this exclusively, but it is a good study tool. So let's look at the first one. The first we're going to talk about is atomic radii. So what we're going to do is we're going to define the terms in the define the term box. Then we're going to talk about increase, decrease, smaller, bigger, and y, and the left to right, and up and down. So the first thing we're going to do is we're going to define this term. Okay, so the definition in your notes, if you want to look it up, is half the distance between the nuclei of 2 identically bonded atoms together. The reason it's not writing, the pen has frozen on me. So give me just 1 second. Hopefully it'll kick back into gear. So again, one more time. Define the term. It is half the distance between the nuclei of 2 identical atoms bonded together. Still waiting on the pen. Okay, so I guess I could just kind of talk about this. Now, if you know that you were in geometry class and they asked you to define a radius, you know that it is half the distance of the circle. So it's halfway across the circle. So again, you can still relate that to an atom because it is a circle. However, the big problem with this is, does an atom have a defined end? Does it have a point where you can say, yep, there's the end of this thing, I can look at it, I can point at it, I know exactly where it ends? No. Okay, the reason we know that is because electrons don't travel in perfect little circles. They travel in something called orbitals. Well, since they travel in orbitals, it's kind of this area that we think it is in, and so we're not quite sure where the electron is exactly located, and so we kind of have to come up with this. They had to figure out a way to create this atomic radii. So the way they did it is just exactly what the definition says. They took 2 atoms of the exact same kind, so we can just pretend, and let's just say hydrogen atoms, because that's a good way to think about it. That way it kind of lessens the load of trying to memorize a fact. So again, let me finish writing this so I can think. So 2. Pen is really slow today, guys. I'm sorry, and if it's lagging in the video, I wish there was something I could do. Excuse me. Of identical I'm just messing all kind of sorts up today, guys. Again, I'm sorry. I'm recording this on a Thursday afternoon, and I'm not going to be here tomorrow, so just kind of bear with me. Okay, so for the 5th time, define the term atomic radii. Half the distance between the nuclei of 2 identical atoms bonded together. So what I want to do is I just kind of want to draw this, and I'm doing dots just to kind of make an effect. And so what we're going to do is we're going to say that that is 1 atom, and we're going to color this the center part in. We're going to say that is the nucleus, and then what we're going to do is we're going to kind of overlap these 2 things, and then we're going to draw the other nucleus inside of the circle. Okay, and so the atomic radius, if you drew a line connecting the two nuclei, it would be half the distance. So from 1/2, this is the AR, or the atomic radius, if you will. It's half the distance. One thing I want you to actually know about this is the unit. Okay, the unit it is measured in is the picometer. And I think I told you this in your notes, but again, it's just something that whenever you can come back and look at this. And that is 1 times 10 to the negative 12th meters. Really, really, really small. Okay, the picometer. Make sure you know that that is what it is. All right, so now let's talk about the trend. I'm just going to write the trend in red, and then I'm going to explain it in purple. So this is kind of what I want to do every single time. The trend is that it gets smaller as you go left to right, and it gets larger or bigger, however you want to say it. It gets larger as you go down a column. Okay, so that is the trend. So remember what you have to do. You have to tell me what happens and then why it happens. All right, so here's the kicker to all of this. As you move left to right, one of the big things is that you are on the same energy level. Okay, so if you're on the second energy level, which is the second period, you remember you have 2s and t. Okay, 2s and 2p. So you're still on the second energy level. The rings are not getting any larger. The rings are staying the same size. All you're doing is putting more electrons on those rings. Okay, but what is that all and powerful, magical word that we have been talking about so often? This comes into play, and that is Zeph. And so what I'm going to do, and this is again something that we're going to have to know a lot about. So what I'm going to do is I'm just going to write it up here. And I told you at the beginning of this chapter, I said I'm going to say this word about 150,000 times, and I probably have at this point. All right, so what this is the effective. You're probably going to want some space underneath this because I got a few things I want to write underneath this. The effective nuclear, come on pen, effective nuclear charge. All right, and so what does that mean? It's talking about the nucleus in general. How powerful is that thing? So the way I kind of define this is how many protons in the nucleus guys, I'm sorry, this pen is not working very well today. Nucleus are pulling on the electrons in the orbitals. Okay. So that is the key right there, is how many electrons in the nucleus, again this is nucleus, are pulling on those electrons out there in that orbital. All right, so again, this effective nuclear charge. So what happens is, since you are on this exact same energy level, your Zeph, you're going to have more. As you go across, you're going to have more protons to pull on more electrons. And again, and it's just like I kind of gave you the example in class. If I have, and again, what I mean by this is lithium is 2p1, and it has 3 protons, and it has 3 electrons, versus in the exact same period, neon. And neon is going to have 10 protons, and it's going to have 10 electrons. But remember, it has the exact same number of rings. It has 2 rings. Well, if you've got 3 pulling on something, or you've got 10 pulling on something, what's going to win? Well, naturally, you should understand that 10 is going to be a lot stronger than 3, as long as the sizes are the same. And the sizes are the same. So what you could actually come in here and put is the same energy level means the same size. Let me change that color to black so you can read it. Means same size. Okay. However, I know that it says smaller. it is in essence going to get smaller, but the rings are the same number. Okay, so the Zeph is going to take those protons and those electrons and it's going to pull it in a little bit tighter. All right, so essentially the protons are pulling tighter on those rings. Okay, protons pull harder on rings. Pull harder on the rings. And again, what is a ring? Hopefully you know by now is an orbital. If you don't, write orbital under that. Okay, so that takes care of left to right. Now let's talk about as it goes down a column. Well, we've already said that it gets larger. So why does it get larger? Well, guess what? If you're going across, it's the same energy level. This time as you go down, you're starting to get on different energy levels. Okay, well, what does that mean for this atom? Well, since you have different energy levels, Hey, just 1 second. All right, so different energy levels. So what that means is since you have different energy levels, that means that you're going to have more electrons. Well, when you have more electrons, what does that mean? You have more space taken up. Okay? More space is used. Okay? So different energy levels means you have more electrons, which means you have more space used. And so in essence, what I'm really getting to is the fact that you have more orbitals. And again, the way we can easily remember this is you're going to have more rings, if you like the word rings. Okay? But technically you are adding orbitals every single time you go down. Okay? So what is a good way to think about this? Well, lithium has 3 protons. Okay, and then it has 3 electrons. And then I'm going to go down to the 6th period. I'm going to go to cesium, CS. Well, it's got 55 of both of those. Okay, so lithium versus cesium. So it's going to have 55 protons and electrons. Well, can 55 protons and electrons fit in the exact same space as 3 can fit in? Absolutely not. Okay, so you have to account for that size difference. Okay, so that is atomic radii. Hopefully you kind of have a gist of what's going on here and how this is going to work, and hopefully that has helped you a little bit. All right, so let's move on to ionic radii. I'm going to clear the board, pause it, and move it up to the next one. Okay, so let's talk about ionic radii. Well, the first thing we need to know is what in the heck is an ion? All right, well, hopefully you know this by now. An ion is an atom that has gained or lost what? That has gained or lost something. Okay, if you said an electron, then you are correct. So it has gained or lost an electron. That is the key there. Now, there are two types of ions, and hopefully you remember these 2 types. The first one is the cation ion. Okay, and what does it do with its electrons? It's going to lose electrons. And what does that make its sign? Hopefully you remember a cation is positive. All right, so what is the opposite of that? We have the anion, okay, or a negative ion. So what is it going to do with electrons? It's going to gain them. Okay, it's going to gain electrons, and what is its sign going to be? It's going to be negative. So again, an easy way to remember these things is a negative ion, and cation has that positive looking plus T right there in the center. Okay, so that is what we're talking about. So one other little thing, and I've used my space wrong here, but it's okay. One thing that I do want you to grasp and I want you to understand are that cations are going to be metals. This is something really, really, really important. Cations are going to be metals. And in that term, I told you this in your notes, it's going to be group 1, group 2, the transition. Okay, and then I individualized 3 of them. And I'm going to explain why again. Aluminum, tin, and lead. Well, the reason I individualized those 3 is because they're not in group 1, they're not in group 2, they're not in the D block where the transition metals are, but they are still metals and they are in the P block. Now, there are other metals than these 3, gallium, indium, thallium, and bismuth. They're all metals. However, we rarely see them. But aluminum, tin, lead, you use every single day. Okay, the next thing, the anion. Okay, all right, the anion, these are going to be non-metals. Okay, these are going to be non-metals. And what these are is groups 15 through 18. Groups 15 through 18. Those are going to be your your nonmetals. One more little thing that I want to point out. Cations, we've already said right here, lose electrons. Well, when you lose an electron, what happens to your size? Your size will go down, because what's happened when you lose an electron? You drop an orbital, you drop a ring. Okay, so there you lose an orbital is the reason your size drops. Okay, so you lose an orbital. Now, so what's the opposite of that? Now, technically, anions aren't really going to gain any size. And the reason why they're not going to gain any size is all they're doing is adding an electron to an orbital that already exists. So kind of technically, you would think it would get a little bigger, however, it does not. And the reason I say that, let's just look at fluorine. Okay, it's got 2 in its first ring, and then it's got 7 in its second ring. Well, how many does it gain? Well, if it gains 1 electron, did it get any bigger? No, it absolutely did not get any bigger. Why? Well, because it already had that ring there. So you're not gaining any size. Okay, so that's just something that I kind of want to mention to you. All right, so let's talk about trends. All right. Technically, what I want you to know is the cation and the anion. Let's change this. Okay, the way I want to say it is it gets smaller as you go left to right. It gets smaller as you go left to right. And there's not really any other way to say it except, number one, the cations are going to lose an orbital. Okay? And then the anions, even though they are, gaining an electron, you're still technically going to you're going to be smaller within the same group. So even though lithium is going to lose and get down to 2, what happens is the fluorine still, when it's charged, is going to be a little bit smaller because it still has those 9 electrons pulling on the center. So it's still going to technically get a little bit smaller. All right. Well, what's going to happen as you go down a group? Well, here's some good news. It is going to increase. Okay, it is going to increase or get larger, however you want to put this. I know I wrote larger in the one above it, so larger is fine. Okay, and this is the best news of the day. The reason it gets larger is the same reason as above. The same reason as atomic. Okay, same reason. So we're not going to have to write all that again. So again, it's you adding more electrons, you're adding more energy levels, you're adding more orbitals, so it takes up more space. That's kind of what I want you to get. The same reason as atomic radii. So hopefully that one wasn't bad. Hopefully that one was fairly simple. Okay, and to me, honestly, this next one is the easiest. Valence electrons. I'm going to pause the video one more time. I'm going to clear it. I'm going to move it up so I can write in that space. Okay, so let's talk about valence electrons. First of all, let's define a valence electron. Okay, a valence electron is the electron in the, sorry about the pen, guys, and I hope the video is not lagging. There's a high potential for some reason, because normally when my pen lags like this, the video lags even more. But again, just kind of stay with me. Hopefully you can kind of bounce back and forth. If you need to write it and re-listen to it, that is perfectly fine. But again, the valence electron is the electron in the outermost energy level. Okay, the outermost energy level. Yeah. All right. Another little fact that I want you to know about valence electrons is these things allow, excuse me, don't put that right there. Please erase that. I need to put something else right there. All right, let's try this again. These allow for chemical bonding. These are the electrons that are actually used when atoms bond together. Okay, so you really need to know that. All right, another good thing that's a very simple topic is the group numbers correspond to the valence number of electrons. So what I want you to do is I want you to write those in. Okay, so group 1 has 1 valence electron. Group 2 has 2. Okay, and this is where it's going to kind of get strange. And I'm doing this in different color for a reason. Group 13. Now, I know what you're thinking, group 13, why did he skip that? Look at boron on the periodic table. That's where we're talking about. Group 13. That has 3 valence electrons. So here's what I really need you to also understand. We skip the D block, or skip transition metals. Now, I'm not going to tell you why. It doesn't matter. You don't need to know that fact. And here's something that I will also tell you the truth. In all my years of chemistry and my learning, I have never learned or heard or talked about valence electrons for the D block, ever. So if I've never heard it, there's no reason for you to ever hear about it, okay? All right, so let's just kind of continue with this trend. All right, group 14 has 4, and this is carbon. Okay, group 14 has 4. Group 15 has 5. And group 16 has 6, and of course you know what that leaves us, and that is group 17 has 7. Okay, all right. There's one more thing that I want to add to this, and hopefully you got enough room to do it, and I'm going to do it in brown, and that is the charge. Now the charge necessarily doesn't, but it does have something to do with the valence electrons, and this is just something for you to, because you're going to have to know it next chapter anyways, okay? So group 1 has a +1, excuse me, let me do this my way. I wasn't thinking there for a second. Group 1 has a 1+ charge, okay? Group 2 has a 2+ charge. And remember, what do we do with the D block? We skip it. And again, and the reason why is because the transition metals, they transition. They can change. They have different charges. Is a plus, did that again, excuse me, I'm not thinking, is a 3+, and this is the one where it gets kind of weird, and hopefully you remember this. Group 14, remember how many valence electrons do they want? Well, they want 8. Well, 4 is right smack dab in the middle, so group 14 actually can go both ways. It is a plus or a minus 4. It can actually do both. And remember, this is where the magical carbon atom is, and that's why it has its own entire branch of chemistry devoted to itself, is because of that reason. Okay, all right, back to the beginning. Continue going. So group 15, this is when it starts to go back down. It is a 3 negative. Okay, well, why is that the case? Well, it has 5 valence electrons. How many does it want? It needs 3 more, so if you gain 3 electrons, you get to your 18. So that is why. So what we're ended up trying to do is trying to add up to 18, okay? So what do you think group 16 has? Well, good news for group 16 is it's 2 negative. And then finally, the one we already know, the halogens, group 17 is equal to 1 negative, okay? So those are your charges. All right, so the final thing. Here we go. What happens as you go left to right? Well, obviously, we just did that. It increases. Okay? The valence number of electrons increase. Okay? Well, again, why? There are more electrons added every single time. More electrons added to the orbital. Okay? More electrons added to the orbital. And this next one, what happens is you go down a column from top to bottom. This is the only one that's like this on this entire sheet, but it's the easiest. Notice what I have done. All of group 1 had 1. All of group 2 had 2. All of group 13 had 3. So if I'm looking within that group, so look at group 1, lithium, sodium, potassium, rubidium, cesium, francium. What is any different between lithium and sodium in the number of valence electrons? There are none. So what happens to that value as you go down? Stays the same. Okay? This is the only one on this entire chart that you can do this. And you really make sure you know this, because I'm pretty sure, and you know, since it's the only oddball out, there is a high likelihood that you'll probably see that again. Alright, so that is the whole entire front of this worksheet. It hopefully should not have taken you very long. Very simple. Monday when I get back, we're going to do ionization energy, electron affinity, and electronegativity. Now those are going to take a little bit longer, a little more discussing, a little more talking. But again, I just wanted you to go ahead and have this so you can understand exactly what we're going to do. Alright, so I hope this was good for you. If you have any questions, don't hesitate to ask, and I'll see you guys Monday.